Okay, this time I remember to record. Okay, so from now on, much of the things I will say will be unique to guide. And so I want to revisit this picture that we last talked about, and that is to predict the type of vehicle. So we want to predict whether the vehicle is an SUV, a pickup, a wagon, or a car, and so forth. There were 6 possibilities. I had shown a similar picture before where we predict the drive type, 4-wheel drive, front-wheel drive, and so forth. So for that one, we found that cart took 36 hours. So over the weekend, I ran this with the R part, the R version of cart. Why we changed the Y variable to the type of car. It ran for 77 hours. So compared to what this picture showed, which is what guide got within less than a second. But I want to say something I forgot to mention, and that is this this node here where we have a linear combination split on length and width. So in the original, the commercial version of cart, so cart has a commercial version. They do consider linear combination splits in addition to univariate split. So there's an option to do a linear combination split. So in the linear combination split, you would have a node. You would have a node like that, and then the split will be summation ai xi I equals to 1 to k less than c. Right. So of course you can set a to be a1 to be 1, and just divide by a1. And in the commercial version of cart, of course, these splits will be much more flexible, and you would think that they're much more accurate. But how do you search for the coefficients ai and that's c, right? With a univariate split, if you have xi less than c, you just search over c because you're already locked onto that axis, and you just search for various values of c to find the best partition. But if you are trying for a linear combination split, there's, at first you think there's no easy way. So the commercial version of cart, which is not implemented in this option, is not implemented in our part for obvious reasons, is they just did a random search. Okay, so they randomly initialize all the AIs. You can initialize them to 1s and search over C. So once you initialize them, all the AIs to be 1, then you have a certain hyperplane, and you just move, up and down, and you find the best C. After you find the best C, then you manipulate A2. You slowly change A2. Each time you change A2, keeping all the other A's constant, you have to find a new C. All right, and then you find the best A2 and the new C. Now you go to A3. You can imagine how time-consuming that is, right? And the answer is not unique in the sense that it depends on how you initialize and when you stop. Okay, so theoretically it can be done, but practically it's useless. So that's why when I too realized the power of linear splits, but I decided to leave it to 2 variables. I don't know if somebody asked, or maybe it was Varun, why don't you have more variables? Okay, if I only have 2 variables, then the splits will be like a1 x1 plus a2 x2 less than equal to c, and then you can set a1 to be 1, right? So that at least you now only search over 2 numbers, but even then that's a lot of work, right? But at least it cuts it down substantially. But that's not the only reason why I chose this. The main reason is I want to show you the picture. With the linear combination split, I cannot show you this high-dimensional space picture. I want to show you the split, so that the split can be shown in terms of a tree diagram, but I want to show you the data points. Okay, so up to now, actually, and I like to remind my students, we have all these fabulous examples of those trees, but I've never seen the data. I've never shown you the data. You don't want to look at the data. It's a big matrix, right? But with a node like that, I can zero in on that node. I can show you this data. All right, and I can only do that if I only have 2x variables. Okay, so that's how I decided to do that. I mean, I could have all the variables instead, but then I have no picture to show, which defeats the purpose of the tree. I mean, the purpose of the tree is to show you something that you can explain what's going on. But on this, even on this point, right? So how do we search for this line? I show you this line, and nobody would quarrel with me that this line is not nice looking. But this line is not unique, right? I could have a line that's parallel to it, and it would have the same, it would serve the same purpose as separating these these points. The line could be like that, right? So how do I find that line? So even if I'm willing to search over all the A2 and C's, right? Even if I want to search over all of them, what is the target function we're trying to maximize or minimize, right? And you can think, oh, how about support vector machine, right? You could use a support vector machine, but that's another search, okay? Besides, the support vector machine doesn't apply when you have 3 colors. A support vector machine is only for a 2-class problem. If you use a support vector machine on a 3-class problem, you will have to do maybe 1 versus the rest. So now you have several support vector solutions to choose from, right? So this is where guide is full of statistical engineering. Okay, I want to use the cheapest things that will work. Right? If one day I quit my job, I work for the automotive industry, I will make a real cheap car that's made of cardboard, but it runs really well and has great gas mileage. Just don't crash it. Okay. So what do I do now? So now you think, what if I ask you to guess what I did? What would you think that I did? What do you think I did here? Well, you can say I'm a one-trick pony. If I'm a one-trick pony, my trick is what? It's LDA. Okay. So what I did is I did LDA on this. So LDA, so now actually we only have a 2-dimensional space. LDA is nothing but a change of axis, still 2 perpendicular axes, right? But change the axis, rotate the axis so that the first axis has a bigger separation of the classes. So these are the purples, and these are the pinks, and there's one orange here, right? So that's what is LDA? LDA is just changing the axis from horizontal and vertical, just rotate them, right? Until the first axis gives you the biggest separation. And the separation is well defined. It's the analysis of variance F-test, which everybody knows, which is very fast to do. I mean, I teach students analysis of variance F-test in the exams, and they don't use computers, they use a pocket calculator. So you can imagine if you now implement a computer, how fast that is, right? So I use analysis of variance. Analysis of variance will tell me to cut somewhere between. And then all I do is just shift that line. That's the only search I did. LDA gets me that orientation, right? So LDA will say maybe cut somewhere along here, right? Then I shift it right and left. Okay, and of course it's not unique, right? I mean there are many places, but I shift it so that I get the closest purple and the closest other color and take the midpoint. So it's aesthetically nice, right? Because so that's all I did. It's very cheap. Okay, but as far as I'm concerned, it does the job, right? And nobody's the wiser, So when I showed this to you last time, nobody complained that the line is doesn't look good. Although, because I'm a perfectionist, I did something more. LDA is not robust. So if I happen to have if this point happens to be here, right, then this LDA direction will change, right? Okay. So what I do? I do something cheap again. I trim the data. So I throw away the leftmost 5% or 10% rightmost. I trim top and bottom. So I trim away the outliers. Then I apply LDA. Okay. And I discovered this through experience. It's not that I'm such a genius. I anticipated this. But once I implemented it, I look at some examples. I find that, oh, for some of them, the lines don't look good. Because you see, for humans, when you look at these pictures, you think that this is reasonable. That's because I think your eye is focusing on the bulk of the middle of the data. Your eye can ignore outliers somehow, right? So that's all I did. Okay. Well, this is just a little slide for those of you who haven't seen the technical definition of LDA. LDA is just an eigenproblem. So you have a data matrix. I have a data matrix for each class for the purple triangles and the pink dots and so forth. And then I take their centroids. So the centroids. So let me choose a purple. So the purple is somewhere here, center is here. And then I take the centroid for the pink. Maybe I don't have a pink, so I have a red. So maybe the centroid is somewhere here. Okay. And the orange is only one. So the orange is itself the mean. And so LDA is, after, of course, you have to rescale things to make the variances balanced. But assuming they are, basically you join, join the centroids. And take perpendicular bisectors. I'm not drawing this very well. Okay. And then once you have the perpendicular bisectors, you can remove this line. You can remove this line. Oops, no, I had that line. So I have a bisector here. So I can remove. Do that. So I can't, I guess if I touch it, the whole line goes away, but basically this is the region for the pink, or for the orange, this is the region for the pink. And this is the region. Yeah, so roughly speaking, if you so-called sphericize the data by normalizing all of them, then once you sphericize everything, you're basically fitting a bivariate normal distribution on each class, right? And so now you have three hills, all have the same dispersion. And maximum likelihood says where those likelihood surfaces cut, which are basically just the perpendicular bisectors of the midpoint. So, but in general, if you think of it in matrix language, you do the within class variance. So this is data minus its class centroid, and this gives you the within class covariance matrix, or short of the nj minus 1 denominator for the jth class, and you sum it over here, and that you get the pooled within class. This is like what you do for analysis of variance, or you do for two sample t-test, you do a pooled estimate of variance. And this is the between, that's why it's B and W, B and between. So this is, the distance of each centroid from the grand mean. Okay, so you calculate those two variances, those two matrices, calculate this matrix, take the eigenvectors. The eigenvectors are the LDA coordinates. Right, and they're very super fast algorithms, for doing this. So this takes a fraction of the time. Okay, we already finished talking about the pruning. Oh, okay, so I want to talk about the SE rule. So, yes. Oh yes, that's right. Yeah, you are right. So actually, that was my first paper, 1988. I did not restrict it to. Maybe I drop it here. Right. So you have if you have 3 classes, I can cut into 3 parts, because here is X1, X2, and here is one class, the blues, and then here's the purple, and this is red, right? So I take the center. So I draw it such that they are already sphericized. Right. So now let me choose another color. Choose orange. Okay. So the perpendicular bisector for this is like that. The perpendicular bisector for this is like that. Right. And all these perpendicular bisectors will meet at a point. Right. So now you cut up your whole space into 3 parts, and that's why you get this 3. Right. And the only thing here is the splits are not of this form. You would think that splits of this form, AIXI, or rather, I think the split is of the form A1X1 plus A2. C, right? But this is so this is less than or equal to, say, 5, and this is bigger than 10, and in between is between 5 and 10, right? It is not. It is not. You classify a point here to be blue because its distance to the center of blue is shortest. So it's not a linear combination, a minimum of distances. So you can draw it as a split with 3 branches, okay? But the split cannot be characterized with one linear combination. It's a distance of whatever point you have to each of these 3 centroids. So it's not so easy for people to quickly understand what's going on, right? So that was the original motivation for me to think of variable selection first, to turn it to one-dimensional LDA. Because I thought of this first, and in the original paper in '88, we actually had this in the paper, but we also had this other thing where we choose a variable first, and then once you choose a variable first, then you don't have X1, X2, you only have X1, right? And then you have your blues are like here, and then the purples are like here. And we have an orange like that, right? And then now I can split on red. So I can split here, right? And then now my split will look like X1 less than C1, X1 bigger than C2, right? So that was what I did. So in 1988, we actually did this. But it has 3 legs, okay? And I was trying to come up with a cheap copy to compete with the Mercedes, the car, which has 2 legs. So, but my first attempt had 3 legs. It's like, I want to compete with Mercedes, but my car has 3 wheels or 5 wheels. Okay, and the number of legs depends on the number of colors, number of the J here. So, but incidentally, so we did in 1988, and then later on 1996 something, we managed to change it to 2 classes. Basically, the obvious thing we did is we just merged, some of these colors so that you get 2 super classes, and then we get a binary split. So we did that. After we did that, many people wrote back and said, "Oh yeah, that's great." But some people asked, "Can I have 3 splits?" After we move away, they started asking that. So then we wrote another paper. There's a cruise algorithm which would have multiple splits. So some people like multiple splits. In a way, I can understand, because if you have 3 classes that are equally many, if every time you have 3, you can sort of follow roughly where the main colors are going, right? Because if you force them to go down to 2 paths, then 2 colors have to be joining in one side, and then after that, they maybe separate something else. So maybe it's harder for some people to look at, but it depends. But we got both of them. Okay, so we already discussed about cross-validation. Okay, so here, this is something that came out from the CART method. So we have cross-validation. So let me show you these trees. So imagine like this, right? So we want to see if we cut here, how good is this tree? Right? If we cut here, how good is this tree? And we get an estimate by using alpha 1 and putting alpha 1 into all these trees to see, if I use alpha 1 to cut all of these trees, then I apply the leave one out data to estimate the error rates. So I can draw this picture. Right? So this is the number of terminal nodes. Okay. And so this is the tree which has no splits. It has a very high error rate. I split it once. So the error rate drops because now I have 2 partitions. I keep splitting, and then eventually it goes back up. I overfit, right? So you would think that you want to choose the minimizer, right? The minimizer actually is here. The black dot. That's one of the minimum estimate of cross-validation estimate. But as this picture shows, it's not always convex, or at least it doesn't always have a, it's not always monotonically decreasing and then monotonically increasing. It goes to the bottom and then it waves a bit because of cross-validation, because of randomness on the data, all kinds of things, right? So the CART solution, I think because they were targeting towards selling the software. I think they didn't say that, but I can understand that. If you really insist on the smallest, here, this picture is a toy example. I have 7 terminal nodes, right? And there is one with only 4 terminal nodes that's only slightly worse in terms of this cross-validation estimate, right? And this cross-validation estimate of error is not perfect anyway, it's an estimate. So the idea is, why don't we sort of like draw a confidence band around the minimum and take the shortest tree within the confidence band. In other words, once you have a confidence band, like here I said KSE, K is the original CART is 1 SE, right? You take 1 standard error around this, and then so if I clean this up. Okay, so if I make this bigger. So I actually have a dotted line. That dotted line is the upper confidence bound. There's another dotted line. But we don't care about the bottom dotted line, right? We just take the upper confidence bound and then choose the smallest tree. So the red dot is the one that's the shortest that's within this bound. So it's like the shortest tree that is almost as good, given that we are not sure that the black dot is really the best, right? So for purposes of interpretation, why don't we just get a shorter tree? Because even if I show you the black one, when you look at it, you're not going to spend a lot of time looking at the lower branches, right? You will be looking at the top anyway, right? Although I should say that in simulations, if you are interested in comparing prediction accuracy, if I want to compare a tree with, say, a neural network or support vector machine, if I use a black dot, I can squeeze out a bit more accuracy. Right, so if you really want to use this as a prediction machine, which is not the best because of all the constraints to make it interpretable, but if you really want to compete, you can squeeze out a bit more accuracy by just using the black dot. Right, so this is called the KSE rule. K is in CART they use 1 SE. Oh, by the way, you may wonder, how do you measure standard error, right? We really don't know what is the standard error. We have 10 cross-validation trees, right? you can average the estimate for each alpha, you cut it. So maybe this one you cut here, maybe this one you cut it here, right? And then so you can estimate the accuracy of this tree after you cut of the main tree, after you cut the bottom one. But what is the estimate of standard error? We don't. So, and the card book doesn't really mention that. How do you estimate standard error? I assume that they just did a naive way. They have 10 estimates, say it's 10-fold cross-validity, right? Then they just use the usual standard deviation formula for the 10. Although that's not strictly speaking valid because these are not IID estimates, right? So as a result, I don't think anybody knows really what this K should be. It depends how you measure standard error. We use the word standard error. It's not really a standard error. We just want to get a so-called confidence band. So after a lot of experimentation, the default in guide is a quarter standard error. Okay. But card uses 1. So I settled with a quarter because it seems to get the best compromise between the size of the tree and the accuracy. Okay, so far I've talked about classification. So so we talk about predicting the type of car, predicting the type of drive mechanism, predicting COVID-19 death or survival. What about regression? Okay, so in CAD, the regression is like one of the final chapters. It's almost like an afterthought. After they develop everything for classification, they apply the same thing, everything to the regression by changing the criterion of impurity. Right? So remember, for classification, the impurity is like a Gini index or entropy function. Right? For regression, you just use residual sum of squares. So everything goes through. Okay. But not for guide or even its predecessors. Right? Guide doesn't use this greedy search. You see, CAD uses greedy search. So everything can be dependent on just impurity. Just search for the best fit that minimizes impurity. But guide doesn't do that. Guide uses chi-square test. In a chi-square test, you have 2 categorical variables. In the car situation, the type of car, the rows of the chi-square are the SUV, sports car, wagon, and so forth. Right? So if there are 6 possible classes, it's a 6 by whatever table. All right. But in regression, I don't have type of car. I have, for example, suppose I want to predict sale price. Okay, retail cost or retail price for the car. It's a continuous variable. So I need to somehow get into. So if I want to piggyback on what I have already done fairly well for classification, right? If I don't want to reinvent a new wheel for regression, the question is, how do I capitalize on what I already done and apply the regression? So that was what I spent a few years thinking about. And immediately after we finished the paper, the 1988 paper, immediately after that, I was thinking about extending the regression, but it wasn't obvious. But now if I tell you, you say it's fairly obvious. So let me just show you an example. Suppose we have one variable x. So x is on the horizontal axis, y is on the vertical axis, right? Suppose the true function is that black curve. It's a very smooth curve. If I use a regression tree, never mind how I find it, but it will look like that. It's a staircase. The red lines are the staircase, right? So this part here is here, right? Negative 1.4 is here, right? This part here is here. Okay, so you cut up the data into this, and then you fit the step function, and that's why you can, if you see it from there, you can see that it cannot be really very competitive in terms of accuracy, right? Sure, as the sample size goes to infinity, the number of steps will grow. So eventually, whatever curve, we can approximate with a very fine-grained staircase, right? But the convergence rate will be slow, right? And so because we don't have smoothness. So for a situation like this, you never need to look at the tree on the right. You can just look at the data on the left, right? As long as I draw you those red lines, you don't need a tree on the right. The advantage of a tree on the right is if I have more than one dimension, if I have more than one X, I cannot show you the picture on the left. Unless maybe I use virtual reality and whatever, but higher than 3 dimensions, you have a hard time, even with VR lenses, right? But I can always show you the tree on the right because they will split on X1 someplace, X5 and someplace else. So that's the advantage. But that's just an aside. But coming back to here, you would think that a better way to split it is to split it once along here and fit 2 lines. Why you spend your time, fitting steps, right? Fit 2 lines. Now, why didn't CAD do that? Because it would increase the amount of computations a whole lot more. When CAD considers this vertical red line, when it fits only piecewise constant, it's just fitting a constant to all the points on the left and constant on the point on the right, and just calculate the variance. That's the result sum squares. But if you ask CAD now to fit 2 lines, so at every cut, fitting a line is no big deal, but every cut for every variable at every level of the tree and in cross validation, that's quite a lot, right? Suddenly, fitting 2 lines is going to cost more in computational time than fitting 2 constants, right? So CAD cannot afford to do that. But I really want to do this because, first of all, this tree now is so much neater. Look at the right tree. Look at this tree here. You look at this tree, if I don't show you the picture on the left, you think that this is something very complex, right? If I just show you the tree on the right without showing you the picture on the left, you see that, oh, so many splits. You think that, oh, this is a very complex thing. But actually, maybe just 2 lines will fit fairly well, at least if you don't have too much data, right? So I want to do something like that, fit 2 lines or planes. I can fit multiple linear regression, right? But I don't want to go through the expense of computing these potential planes for every possible split. Okay, so how do I get around that computational problem? Here's what I do. So in 3 lines, I fit a model to the data and obtain the residuals. Okay, so in this picture here, I just fit this purple line. Right? I fit this purple line. Only 1 fit, not 2 fits for every possible split. I only fit 1 model to the parent node. And then I get the residuals. So let me show you a picture. So suppose my surface is like this, very, very symmetric, all right? So you don't see this parabola. You see these bubbles, this data above and below, right? I want to fit this with 2 planes, okay? So if this is a V, it's even better. The 2 planes will be pretty good, right? But it doesn't have to be V, but so something. So let me ask you now, we are going to split this. We know that this thing is curved. It's not flat. We know that it would be better if we split somewhere and have 2 planes. Should we split front and right, or should we split front and back, or left and right? In other words, if this is x1, should we split along x1? And if this is x2, should we split along x2? If you split on x2, you just get back 2 parabolas. It's worse than the first parabola because now you have half sample size, right? So you want to split this way. And then I ask my students, how do you tell the computer to see this? See, all the students I teach, when I show them this, they all agree this is the right way to see it. That's because they are using a very powerful neural network, which consists of the eye and the brain, right? They can see that. But how do you tell a computer to see this? Well, if you fit a plane to the original data, you will see the positive residuals are in the center. Negative residuals are the two rights, to left and right, right? So you see a clustering of the positive residuals in the middle and the negative residuals on the left and right. But if you look at it this way, the positive residuals are all uniformly distributed on top, and negative residuals are all uniformly distributed bottom. There's no clustering anymore in this direction, right? The computer can find that. Computer doesn't need eyes. So this is a picture, right? This is the similar picture. The one picture on the left is the x1. The one on the right is x2. Okay, all right. The red line is the fit that determines which are positive and negative residuals. So the x's are the positive and negative residuals, right? So if I fit a plane to the data like that, I'll get the picture on the left, and all I do is tell the computer to count. So there are 18 points here, and there are 52 here. There are 49 here, and there are 31 and so forth. Over here, I have 37, I have 34, I have 41, and so forth. I just calculate the chi-square, and this p-value is 10 to the minus 14. This p-value is 0.7. I've taught the computer how to see. Right? It's just checking to see whether there's any correlation or association between the signs of the residuals and the values of the x variable. Now I have a chi-square table. So before that, my rows are like SUV and car and wagon and so forth, right? Now my tables only have two rows, positive and non-positive. The columns are the usual before that, the predictor variables. And now the whole machinery goes through. Not only that, because I work on residuals, I can fit very complex models to the parent node. I'm not limited to simple linear regression with one x. I can fit multiple linear regression. I can fit quadratic models. I can fit generalized linear models. I can fit Poisson models because I'm living on residuals. Right? So that's saying that necessity is the mother of invention, right? I had a necessity. I wanted to extend everything I developed for classification and make it applicable to regression. So I need to get this kind of chi-square tables to do variable selection, right? And because of that, I thought of residuals. But once I found that the residuals work, suddenly the concept of residuals is so general. I'm no longer limited to piecewise constant models. That's why in subsequent lectures, you'll see that Guide can fit very, very powerful, very sophisticated models with very fast speed. Right? You see, I'm not fitting these models for every potential cut. Right? Because you try to split a node, you have a parent node. Right? Most algorithms look at each possible cut, and then if you want to fit complex models, they fit one complex model to each of these temporary subnodes, find out how good it is, then move the cut, fit again. Right? You wait forever. I only fit one complicated model. Okay? I don't fit more than one complicated model. You see, that's why. So sometimes when you have a need to do something, you can come up with some ideas that actually will transcend computational power. You can say, okay, oh, you are fast, but in 2 years' time, CPU will be faster to catch up with you. You cannot catch up with me because my concept is so different, right? If CPU speed improves, it will also improve for me. It does not improve for other people and not improve for me, right? Okay, so yes. Oh, for quadratics, so suppose I fit a piecewise quadratic. So here's my y, and here's the x, right? So suppose my true function is like that, right? Now I fit a piecewise quadratic. to this data. Something like that. Now my positive residuals are here. And my negative residuals are here. Right? So suppose this is x1. Right? And x2, x3, they're all random. So really you should split on x1. But now if I do a chi-square table, I catch x1. I will catch x1 because here is like the surface is like this, right? No point to cut here because you just replicate the problem, make it harder. You should just destroy this thing and fit maybe two quadratics, right? So maybe in the end, if I do one split, maybe here I will, if I do a split, maybe I'll split here, and then I will do a quadratic here and I do a quadratic here. Right? So my orange is approximating my red. The red is the truth. Okay, but this is just one split. If I can have more data, I get more and more. So now I'm approximating my curve with piecewise quadratics. If it's actually very close to quadratic, I will still split, but pruning will pull me back. Yeah, so if the true function is really like that, I will, when I first grow, I don't care. I just keep going, right? And then the pruning will say cut, 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 and this is the best. So I regain my quadratic. Right? So the pruning is very important. Okay, if you don't do pruning, cross-validation based pruning, if you do some sort of stopping rule, you may not get it as well. So the cross-validation is a part that takes time, but you save time elsewhere. Okay, to spend the time here. There's some things that you have to spend the time, otherwise everything will be not so good. Other things you can go cheap, right? Okay, so I just use guide to finish the job. Okay, so guide can fit piecewise constant, multiple linear, stepwise linear. I can do stepwise linear regression on every node. I can fit best simple polynomial, meaning that I can fit at every node. So at this node, I can fit y equals to a plus b a x plus x1 plus cx squared if I want. And over here, I can fit y equals to d plus x2 plus sorry, that's not x2, right? So I can fit piecewise quadratic, but each quadratic is a different variable. I can do that. This is already in the software. It's been here for many years. I can fit, when I say simple means only one x, but polynomial in that x. Best analytical variance means the same thing, but you can add dummy variables for categorical variables. That's analytical variance. This is sort of standard statistical models. I can fit using least squares. I can fit using least median of squares. All right. Least median of squares is the most robust kind of this linear regression. The breakdown point of a least median of squares. So in other words, you have data and you want to fit a line. Okay. You know that for least squares, you move any point, anywhere, the line will move. If you use the criterion least median of squares, you have to move 50% of the data before the line moves. Okay. So least median of squares is literally least median of squares. Least squares is actually least mean of squares. Okay. So I don't know if anybody uses it, but it's been there for in the software. Then you can fit quantile regression. You can fit median regression, 90th percentile. You can fit Poisson regression, proportional hazards regression with censored data, multi-response, longitudinal data. So some of these things we'll talk about later on. And so as far as the software is concerned, the predictor variables can be used for model fitting only. So you can say, oh, I have this variable. I don't want it to use to split. So for example, in a medical or clinical trial data, you have demographics, right? You have health conditions of the patient, but you also have treatment. did you get the vaccine or not, right? In that situation, that treatment, if it's 0, 1, 1 if you get the vaccine, 0 if you're not. You don't want it to be used to split, because once it splits, then all the treated go to this side and all the untreated go to the other side. What you want is look at the treatment effect within the demographic groups, for example. So now you want to make the treatment variable used only for fitting in the linear model in the nodes, but not for splitting. So there are two things. There's fitting and splitting. Sorry, I think you had a wrong. Yeah, I realized I made a mistake. When I say splitting means it used to split the nodes. Okay, fitting means you fit the linear models or whatever models you want, or you can use them for both. So I won't have time in this lecture to demonstrate the model, the software, but you can sort of differentially, direct the attribute the roles to each of these variables. Okay. So all right. So the next thing I will talk about, since I only have about 5 minutes left, is missing data. Missing data, in my opinion, is the most difficult problem in statistics. Okay. Many people don't care about it. You look at machine learning. How many machine learning people worry about there being missing values in the data? Especially people in machine learning theory. They don't care about that, because it's impossible to deal with missing data in machine learning if you try to analyze machine learning models. If you want to do that, you first have to model the missingness mechanism, right? You have to model the missingness mechanism. With what probability and when does it happen that this variable will have a missing value? So before you can even start to analyze a machine learning algorithm, you have to, deal with this missingness. So there's a lot of people working on machine learning theory, but I don't think anybody is working on anything that's applicable to data with missing values. But missing values is a reality. Okay. So when I review grant proposals, especially from people in engineering who are applying deep learning, they always say, electronic health records. That's my application. To me, they have not seen electronic health records. They are full of missing data. Right? How do you apply deep learning to data with missing values? Okay, so I think the most interesting contribution of Guide now is we can handle missing data. How people do missing data is the following. They impute the missing values, right? Then they can put in the algorithms. Then the data are complete, right? But sometimes it makes no sense to impute the missing values. So here's an example. Consumer expenditure survey. Okay, this is in the United States, there's a Bureau of Labor Statistics. Every 3 months, they do a survey, national survey. They take about 25,000 people. They're called consumer units. And they ask them a bunch of questions to get an economic pulse of the nation. And so about 2014, 2015, I was invited to visit the Bureau as a resident researcher to see what I can do with Guide. I had given a series of talks like this at Washington, D.C. a few years before that, and some of the people from the Bureau attended, and then they say, oh, you can handle missing data, you should come help us. So I went there. And I went there and asked them, why don't you give me a data set to test this? And they said, oh, look at this data set. And I said, what is the Y variable you want? So they said the Y variable is the interest and dividends that you received the last year. So the variable name is INTRDVX. Okay, so there's a Y variable. And there are a total of 500 plus variables in the data set. And they are missing values. And they have what is called a missing value flag variable. So in this survey, when a value is missing, it's not just coded as missing. There's a sibling variable with an underscore beside it. So this underscore, right? So if the name is this, the missing value flag variable is this with the underscore. That gives you the reason why it's missing. And there are 4 or 5 codes. One is these are 5 codes. A is valid non-response. Response not anticipated. Okay. B is invalid non-response. So like, what is your age? My age is -10. that's invalid. Then they will change it to missing, and they give a reason, right? C is don't know or refuse to answer. This is what we normally think of as missing values. They don't want to say. D is a valid data point. So you still have this code for correct value for the D. And then it's top coding. Top coding is to protect privacy. So they ask a lot of questions, including income and interest and dividends and so forth. So the very rich people would not want to be identified. So what they do is that for every variable, including age, they take the top 2.5% or 3%, all right, of the respondents who give the answers. They take the average of those top 3% and replace everybody in the top 3% with that average. Okay, so all you know is that these are in the top 3%, but you don't know how high it is, average. Okay, that's called top coding. So if you did that, there's a T. So about the top 3% of each variable is top coded. And there are lots of variables with missing values. Of the 500, 124 have missing values. That's 20% of the variables. All right. Of the 124, 67 are missing more than 95%. Okay. Most people will throw away those variables, those 67 variables. In fact, when I submitted the paper, one referee said, why would anybody include a variable that has more than 95% missing values? Okay. My answer to the referee is because I can. You throw it away because you cannot deal with it, right? I can deal with it. So in the end, the data set has got about 4,000 over observations. About 2/3 are non-missing the Y value. 1/3 missing the Y value. I want to find the average for the Y to estimate the population mean, right? So, okay, I'm out of time. So maybe give me 1 minute, and this is a histogram of the data. So this is what is very skewed. This is a Y value, right, histogram. And this is a 100,000. It's 100,000 only because it's truncated, top coded. Some of them get even higher. So, okay, so let's look at this. Age of reference person. The person who answers the survey. This is a proportion missing, right? Proportion is missing. So 0. Everybody has an age because it's a person-to-person interview. If you don't know your age, they ask you to look for your identity card and birth certificate, they can figure it out. Age of spouse, 41% missing. 41% of the sample is missing age of spouse. The same 41% is missing education of spouse. Why are these people, so reluctant to tell you how old is their spouse? Or how well educated is their spouse? Why? They don't have a spouse. Now you impute. You impute. Your data now no longer looks like the population. Right? Okay. So let's look at some others. 84% are missing on IRAs, retirement accounts. 84% are missing. Bracket range of bank accounts. So they ask you how much you have in the bank, but for people who cannot remember, they have ranges. 0 to 5,000, 5 to 10,000, 10 to 20,000. You choose a bracket. Okay. So this is an ordered categorical data. The first bracket may be coded bracket 1, second bracket coded 2, but they are not equal lengths. Now you apply linear regression. Do you want to follow those coding? Right? But the 3, you don't have to worry. If the cut is between brackets 2 and 3, it's between 2 and 3. If the cut is between 4 and 5, it's between 4 and 5. Right? You don't have to worry about a metric as in linear regression. Total value of bank accounts 1 year ago, checking CDs. These variables are important variables because we're interested in how much interest and dividends you got last year. Right? You would think this is more important than the age of the spouse or your age. These are financial variables. We're trying to estimate or predict financial variables. Median value of bracket range for This retirement survivor benefits, 99% missing. Survivor disability, 99% missing. Royalties from estates and trusts, 97%, and value of stocks. This is the principle from which we are trying to estimate the interest. The Y variable is interest and dividends, right? Interest and dividends will come from stock. 99% missing. You throw it away, you throw your, you think you'll be throwing away something very valuable, right? So, okay, I'm out of time, so I don't want to delay you any longer. So we'll tell you how we deal with it. Okay, next time. All right, thank you. No, this is difficult. They do it every 3 months, and it's always the same. You know, basically, people don't have this stocks because maybe they really don't have any stocks, and so they leave it blank. So they get an A missing value flag. You know, non-response, valid non-response. You code it with 0. It's like somebody did not earn any money or somehow lost all their money. You see, so there's a very fine distinction there that you will blur it if you try to impute. Okay, all right.